Hello everyone, my name is Mohammed, and in this presentation I will demonstrate to you how to use SigmaSpectra in your project. So in your project, you will be using SigmaSpectra to select a suite of earthquake ground motions that fit on average your target response spectrum. And once you have this suite of ground motions, you will use them as an input to your 1D side response analyses. The use of Sigma Spectra can be simplified into the following steps. First, you will compute the target response spectrum, and note that this will be done externally outside Sigma Spectra because Sigma Spectra does not compute the target response spectrum for you. You have to compute it and then you simply copy and paste it into Sigma Spectra. The second step is to create a library of ground motions that are suitable for the design spectrum you computed in step one. So additionally, you have to also tell SigmaSpectra what is the library of possible ground motions to select from them a suite of ground motions that fit your target. So once you've computed your target response spectrum and you created your library, that is when we will use SigmaSpectra to generate a number of potential suites of motions from the library created in step 2 that fit on average the target response spectrum you computed in step 1. And usually you will compute a number of potential suites and you will evaluate them, assess them, and ultimately pick the best one based on your engineering judgment. So finally, you will select a suite and this single suite will be used in your analysis. And in this presentation, we will go over all of these steps in detail. So first, we will provide you with a document on how to download and install Sigma Spectra, and you will simply go into this link and that will show you several files that you can download. And in this document, I provide detailed instructions on how to know what is the suitable file based on your operating system. So once you know which file you have to download, you simply click on it and then open it and go through the installation steps, and it's pretty straightforward. So once you've downloaded and installed Sigma Spectra, you will navigate to where it was installed. In my case, that's where Sigma Spectra was installed. And you will see these files and folders. So this doc folder, this includes the manual, and I encourage you to take a look at the manual. They have a very nice, simple example, and they have detailed instructions, which are really helpful for first-time users. And to actually open Sigma Spectra, you will double click on this icon over here, sigmaspectra.executable. If you want, you can create a shortcut to it on your desktop, and that will make it easier to access Sigma Spectra. But this is the window that will open if you click on this icon. So Sigma Spectra has four windows. It has the target response spectrum on the top left side. Below it is the period interpolation. And then on the right, you have the library of motions and its options. And then at the bottom right, you have the calculation window. And we will talk about all these in this presentation. Remember, the first step we said was to compute the target response spectrum, whether it's a code-based or uniform hazard spectrum. Anything is acceptable, and you can import both or any type into Sigma Spectra. So once you compute your design response spectrum, you simply copy it and paste it into Sigma Spectra. So let me show you a demonstration. So in this Excel sheet, I have two different response spectra. I have one that is based on the uniform hazard spectrum, and it's this smooth design spectrum. And to the right, I have another one that is based on the International Building Code provisions, and it is this boxy design response spectrum. And as I said, both are acceptable within Sigma Spectra. So what you would do, you would simply go over here, copy the values, select them all, copy them, go to Sigma Spectra to this white space over here under target response spectrum, right click and select paste. And now you can see we have our target response spectrum. You have to specify the oscillator damping, which is 5% in our case. That is the default value, and that will be the case most of the time. The first column should always be the period. So when copying, make sure the first column is the period. The second column is the spectral acceleration in units of gravity. And then an optional third column is the standard deviation at each period. So in addition to telling Sigma Spectra, I want to target a certain spectral acceleration at this period, you can also specify a target standard deviation, meaning you're telling kind of Sigma Spectra, I want my suite of motions to have this much sigma at this period. But this is an optional input. And for example, for the international building code provisions where you have boxy type design response spectrum, usually will not have a standard deviation, and that column will all be zeros. And that is acceptable. That will not create any problems within SigmaSpectra. And as I discussed over here, that is acceptable for the International Building Code Design Response Spectrum simply because in this case, the target spectrum was based on probabilistic seismic hazard analyses, which inherently include a treatment of the standard deviation. And thus it is acceptable to have a zero standard target standard deviation. But in other cases, such as the uniform hazard spectrum, you might have a standard deviation, such as in this case. So we will copy this. And again, the same procedure. I will remove this, right click, paste, and now I have the second target response spectrum. First column is the period, second column is the spectral acceleration, and the third column is the standard deviation, the target standard deviation at each period. But in your project, you might not have this column, so it will all be zeros. So in both cases, I had like for the uniform hazard spectrum, I had 28 periods. For the International Building Code design spectrum, I had 37 periods for my design response spectrum. But it is actually recommended that the design spectrum be provided at 100 periods in log space. And the actual recommendation is to have 25 periods, at least 25 periods per log cycle, meaning if your design response spectrum, you have like the range of periods is between 0.01 to 10, that is 1, 2, 3 log cycles, to have at least 25 per log cycle. So 25 times 3, that would be 75 points recommended. So I would just say for your project, use around 100 periods in log space for your design response spectrum. And there are two ways to define these 100 points. One way is to simply, like I had this response spectrum which had only 28 points. So when I paste it into SigmaSpectra, I can click this interpolate period box. I can check it, and that will allow me to interpolate the design response spectrum within SigmaSpectra. I can specify the spacing, whether linear or logarithmic. I will select log. I will go from 0.01 second. I will go up to 5 because that's the maximum period in my design response spectrum. And instead of going 100, I will select 65 in this case because I'm not going up to 3 log cycles. So that is one way to interpolate your design response spectrum and have 100 periods. But that is not always recommended. Specifically, if you have a design response spectrum that is similar to the one by the International Building Code, meaning it looks boxy like this, it is recommended that you do not interpolate within SigmaSpectra. So if you have in your project a design response spectrum that is based on the International Building Code provisions, do not interpolate within SigmaSpectra, meaning you have to go over here and uncheck this box. Do not interpolate within SigmaSpectra. And the reason for that is the interpolation scheme within SigmaSpectra does not work well with this shape of design response spectrum. It works well when you have a smooth transition within the response spectrum rather than a boxy shape. So you have a boxy response spectrum, do not interpolate, uncheck this box. What you will alternatively do is when actually developing your response spectrum, in Excel or wherever, here you should have 100 periods. Here you should calculate the design response spectrum at 100 periods that are equally spaced in log sales, and you simply copy these 100 points and you paste them into SigmaSpectra. But in my case, I am now using this design response spectrum, which is smoother. So I will select the interpolate option in SigmaSpectra. But again, for your project, if you have an International Building Code design response spectrum, do not interpolate within SigmaSpectra. Calculate the design response spectrum with 100 points outside SigmaSpectra, and then copy it and paste it with these 100 points and uncheck the interpolate period method. So now we have pasted the design response spectrum with an appropriate number of points into SigmaSpectra. So the next step is to develop a library of potential motions. So that is the next step. And The first thing to do is you have to perform the aggregation of the hazard at your site, and that will give you what is the dominant earthquake scenario or scenarios that are driving your hazard. And the reason for that is you ultimately want to select ground motions that match the design earthquake that is driving your hazard. You want things to be consistent. If my site, the hazard at my site is driven by an earthquake with a magnitude of 7, I want to select earthquakes and design for earthquakes that have similar magnitudes. I don't want to select in my design earthquakes with magnitude of 5. So that is why you have to perform the aggregation, get the dominant earthquake scenario at your site, and then select a library of motions with magnitude range, distance range, etc. that match the scenario revealed by the deaggregation, and we will talk about this more. So to select the library of motions, we will use the Peer NGA West database. And I have another document with instructions on how to develop your library. And you might have gone over these in class, but we will go briefly over them again. You simply go to this link and you will get these documents, and you click on NGA West 2. I'm already signed in, I will sign out. So I'll click on NGA West 2, and you simply sign up if you don't have an account or sign in, and this window will pop up. You will select the no scaling option at default, you click submit, and then you will get these two boxes, suite to the right and search to the left. We will leave the suite as default, so this will only control how the results will be plotted, and we're not gonna care about that, so leave things here as default. What we care about is this search box. So this is where we will specify our search parameters based on the deaggregation. This is where we will tell, I want motions that have this magnitude range, this distance range, etc. So first you can select the fault type. What type of faulting mechanism? I will go with all types. And then for all of these, which require a range, you will simply specify the minimum value, comma the maximum. Let's say that the aggregation revealed that the dominant earthquake at my site has a magnitude of 7. So I will go probably between 6.5, 7.5. Sorry, I'm not writing. 6.5, 7.5. And then for the distance, you have two options, RGB and R rupture. And let's say the dominant earthquake had a distance of 30. So I will go 10 to 50 for both distances. And then another critical parameter is V as 30. So to put things into context, you have developed a design response spectrum, I believe in your case was for site class B, rock conditions. So that is one. Two, this design response spectrum is consistent with the conditions at your site you are investigating. So the bedrock at the site is consistent with this design response spectrum. And that is where you will be inputting your ground motions. So we will input the ground motions at the bedrock level and then propagate them through the soil to perform 1D analyses. So you want to select ground motions that are consistent with these conditions, that are consistent with the design response spectrum, that are consistent with where you are inputting your ground motions. I am inputting my ground motions at the bedrock level, and I have a design response spectrum that represents site class B, bedrock. So I want ground motions that also have been recorded at similar site conditions, meaning at rock conditions. And that is specified using the VS30, the average shear wave velocity in the top 30 meters. So if I'm inputting my motions at the bedrock at the site, I will also select motions that have been recorded at similar site conditions by specifying this VS30. So in this case, I'll probably go between 650 to 1500. And then you can specify a range of duration of interest. I will leave that empty, meaning any durations are acceptable. I will select pulse or no pulse, and then you can also tell the database that I want a specific number of maximum records. I will leave that empty. It's recommended you leave it empty at first to see how many ground motions will fit your criteria. Once you've developed the criteria, you click search records. So now we will get a summary of the ground motions that fit the search parameters we defined up here. First, you will see a plot of their response spectra, and below that, you will see a table with a summary of all events. So here we had 35 ground motions that fit our criteria, which is an acceptable number. So ultimately, this will be an iterative process, meaning you will go back and forth between the search parameters and how many ground motions meet the search parameters to ultimately get enough gram motions. Let's say, for example, you started with more strict ranges, smaller ranges for magnitude. Let's say between 6.7 to 7.3. And let's say you started with VS30 like above 700 and you hit search records. So that was your first search criteria. If you scroll down, we only obtained 7 gram motions that fit this criteria. And I believe for a project, you are required to have a suite of 7. So now you are obliged to only use these 7 motions, regardless of whether they fit your target response spectrum or not, which my guess is not ideal. So you ultimately want to have enough gram motions in your library to select from them 7 that fit your target response spectrum. So probably you want to at least have 20 gram motions. So if based on your search criteria, you didn't get enough gram motions, go back and relax your search criteria to get more gram motions. But at the same time, you don't want it to have like 100 gram motions. That's probably too much in your library. So I'm going to relax these again. Probably I have to change VS30. That will not help much. Oh, I have 15, which is probably still not ideal. You'd like to have more than that. But so I'm going to change this again. So now I have 23 gram motions, which is acceptable. So now what we're gonna do is out of these 23 motions, we're gonna select 7 that on average fit our target response spectrum. So once you have a number of gram motions that fit your criteria that you're happy with, you click on download time series records, then you click OK, and then you click OK. And this will download a zipped folder with the time records for all of these gram motions that fit your criteria. And then you'll just navigate to where this folder was installed and been downloaded, and then you simply unzip it to get an unzipped folder with the gram motions that fit your criteria. So now you go back to SigmaSpectra and you have to specify or tell SigmaSpectra, this is the library of motions that I want to select motions from. So you simply click on select path, and you navigate to the folder where you downloaded this file and unzipped it. In my case, it's this peer nga records underscore unscaled. You click on it, you click select folder. So now SigmaSpectra knows where the gram motions are, where the gram motions exist. So the first thing to check is this tab, motions found. So this will tell you how many gram motions did SigmaSpectra find in the path that you defined. And that will be greater than the number in your table over here. Simply because like if we have 23 gram motions in this table, remember each gram motion is recorded on 3 components, 2 horizontal and 1 vertical component. Meaning, if you open the folder you downloaded, it will have 23 times 3 files. Probably it also has velocity and acceleration, velocity and displacement, but we will only look at acceleration. So you'll have 2 horizontal components and 1 vertical for each ground motion. SigmaSpectra ideally should only read the horizontal motions because we never or we rarely consider vertical motions in our design. So ideally, you would want to have only horizontal motions, and that will be the number reflected over here. So SigmaSpectra is telling us it found 31 gram motions, 31 horizontal motions in our library. So the first number to specify is the number of motions in the suite. And that is probably in your project, you're required to have 7 motions in your suite, so you will leave that as 7. I will skip the seed combination size for now, and I'll come back to it in a minute. The second option is the number of suites to save. Remember, I said towards the beginning of my presentation, we will generate several potential suites. We will look at them, we will assess them, and then ultimately select the one that is best based on our engineering judgment and use that suite in our analysis. So in this case, we're telling SigmaSpectra to give us the best 10 suites so that we can look at those 10 and choose one of them. You can change this number if you want, but 10 is a good number. Another option within SigmaSpectra is to combine components. You can click on it or unclick on it. Remember, we have 2 horizontal components for each earthquake. So if you click on combine components, what SigmaSpectra will do internally, it will combine those two horizontal components from the same earthquake into one. And that is generally the case when you're doing directional analyses. For 1D response analyses, it's recommended that you uncheck this box and you click one component per recording station, meaning only select one component from each station, such that if you selected the north-south component, it will not consider the east-west component, etc. So click this one component per recording station box. So the next step is to actually look at these ground motions. It's always a good idea to click on this flag motions, so that will give you a summary of your ground motions. To make sure you only have horizontal motions and to make sure SigmaSpectra did not read vertical motions. Ideally it should not, but sometimes it will. If you look at this window over here, like it says skipping vertical, meaning it's not reading the vertical component. But sometimes those vertical components are read. So you have to make sure you disable them. And to do that, you simply click on this flag motions and that will open a new window. And you can see each row is a different earthquake, and you can see the acceleration, time history, velocity, and the displacement. So in the second column, that is the name of the earthquake, and that's where in the first column, that's where you can flag different earthquakes. For example, let's see. If you look at here the name, this says vertical, VER, means SigmaSpectra didn't recognize this as a vertical component. And what you have to do is to disable it. You don't want to have vertical components in your library of motions. Make sure to click on flag motions and go through the names and make sure you don't see like something like up or vertical, because that will imply that this is a vertical component and that should not be part of your suite. You only want to have horizontal components. So what I will do in this case, I will click over here, double click on unmarked, and that will provide you the option to click disabled. So that will disable this motion, meaning SigmaSpectra will no longer consider it when selecting the suite. You have other options to choose from. Sometimes like you are interested in a certain earthquake and you want to have this ground motion in your suite. So you can double click and click required. That will make sure that this ground motion is included in your suite. For the sake of your project, do not do that. Another option is, instead of clicking required, is to click requested. So let's say I click requested at these three motions. So now I have three requested, one disabled. I will click close. So SigmaSpectra will provide me a summary of what I just did. It will say required 0, I didn't require any. I requested the 3, but I disabled 1. When I disabled 1, remember I had 31 motions, now I have 30 because 1 was disabled. So it got less by 1 motion. Regarding the requested motions, you have this option, minimum number of requested motions. So I've defined 3 requested motions. I can tell SigmaSpectra, I want a minimum of 1, meaning I want at least one of these 3 to be in my suite. You can specify 2, meaning you're telling SigmaSpectra, at least have 2 of these 3 motions in my suite. But generally, again, for your project, leave everything as unmarked, meaning like it's unflagged, but just make sure to disable vertical components. So I'm gonna turn them back to unmarked, and I disabled the single vertical component that I observed, and I can click close and everything. 0 required, 0 requested, 1 disabled, that is good. So now I have 30 motions, and out of these 30 motions, we want to select a suite of 7 motions. So how can we do that? So one way, like the most obvious way, is to just simply check every possible combination of 7 motions from these 30 and then ultimately pick the best one. But turns out that that's not the ideal way to do it. That is computationally extensive and it would take days, if not months, to check every combination. So we had to pick another method. So just to put things into context, let's say that you have k motions. In our case, it's 7 motions. And let's say in your library you have n motions, and let's say in SigmaSpectra we have 30, but let's say over here I have 42 motions, which with each circle representing a motion. So I have 42 different motions, and let's say we want to check all combinations of 7 motions out of these 42. If you remember from your math and stat classes, you can obtain this from this equation, combination of 42, 7, and it's simply 42 factorial divided by 7 over 42 minus 7 factorial, which would be 27 million combinations, meaning I have 27 million combinations of 7-gram motions from 42. And if you want to get the best one out of these, you have to check every single one of those 27, which will take days to months. So that is not the way we do it. That's not how SigmaSpectra does it. An ultimate method that will still give you a reasonable result, but with much fewer number of trials, is instead of selecting the best 7, select a fewer best number, and that is what the seed number is. So you're gonna first define a seed number. And let's say, for example, in this case, it's 2. And you will tell SigmaSpectra, find the combination of find all combinations of 2 ground motions. And using the same equation we had before, we're just replacing 7 with 2 in this case. And this significantly reduces the number of trials, but that is not everything. That's the first step. So SigmaSpectra will check every combination of 2 ground motions from these 42. And in this case, it is 861. So far, I only have 2 gram motions, but I want 7 in my suite. So what will happen next is SigmaSpectra will check the remaining motions, all of the remaining motions, in which in this case I have 40, because I had 42, I selected 2, so I still have 40. It will check each one of these remaining 40 and add the motion that gives the lowest error, one by one, until you reach a total number of 7. So meaning I first selected 2. And then I'm going to look at the remaining 40 and select this one. This one happens to give me the lowest error. So I will add this one. And to do that, I only have to check 40 times because I only have 40 motions. So now I have 3. And then I will repeat to include 4. So now I only have to check 39 remaining. So now I have 4, and then I repeat that 5, 6, 7 until you ultimately get the target, which is 7 motions in your suite. But remember, like, you have to do that for every combination of 2 motions, meaning the total number of trials will be like 861 times 40 times 39, etc., etc. But this turns out to be much, much, much faster than checking all possible combinations of 7 motions. And you can specify how many seeds you want, meaning the lower number of seeds, the fewer number of trials. So let's take a look at SigmaSpectra actually. So that is the seed number over here. So that is the number I introduced over here when I said I want to look at only the best 2, all possible 2 combinations. So that is defined by this seed number. And which is the second input in SigmaSpectra. You can put 1, you can put 2, you can put any number less than 7 or equal to 7. If I put 7, that is simply as if checking all possible combinations, like nothing has changed. So you have to pick a seed combination size that is less than the number of motions in suite, because if you said 7 seed combination, then in here, you are still doing the same thing as before. You are checking all possible combinations of 7 motions, which we did over here. So you want to pick a seed number that is less than the number of suites, or number of motions in your suite, which is 7 in our case. So if I click 6, look at this. So I have 7 motions, I have 30, and SigmaSpectra actually will tell you the number of trials it has to check based on your parameters, based on what you defined. So if I click 6, look, this number is gonna change. It's always gonna get less and less. So if I reduce the seed number, it goes down, it goes down, it goes down, it goes down. And ultimately you get the fewest number of trials if you select a seed number of 1. So if you select a seed number of 1, what's gonna happen is First, you'll only have 42 possible options because we have 42 motions. And then for each one of these 42, you're going to keep on adding one until you get the best answer. So like the total number of trials will be 42 times 41 times 40, etc., up to like 7. And that will be much, much, much fewer than checking all possible combinations. However, the drawback is that you will not get the best solution. But is it worth it? That's the question. And we are engineers, so we have to select something that's practical, something that's reasonable, but still gives you a good result. And people have done research on the seed number. And as I said earlier, larger seeds, more trials. And it's generally recommended that you have a seed number between 2 to 3. And as you can see in this plot, so like this solid black thin line, that is when every single possible combination was checked using the rigorous approach. So, and that's its root mean square error. And you can see that with a seed number of 3 or even 2, you really get very similar root mean square error. So a seed number of 2 to 3 is recommended, and it's generally you're not significantly losing, you're still getting a reasonably best result, but with much, much, much less fewer trials. And that is the idea of this seed number. The project, again, use something between 2 and 3, and that will give you reasonable time for checking all the trials. In my illustration, I'm gonna go with 1 because that has just fewer trials for things to run faster. So now we've finished steps 1 and 2. We've defined our target response spectrum, and we've defined our library of motions. We have excluded vertical motions. We have set the number of motions in the suite. We have set the seed number, how many suites we want to observe, etc., etc. The final step is to click on this compute. And then a new window will pop up with the results. So remember, we told SigmaSpectra we want to look at the best 10 suites, and thus over here we have 10 rows corresponding to 10 different suites. And on the right side, you can see a plot of the response spectra of these suites. So actually, the blue one in the middle, that is the target response spectrum that I inputted from here. Like I copied this and pasted it. That is this blue response spectrum. And remember, we had a standard deviation. That's the median plus 1 sigma. And then that's the median below 1 sigma in blue. So everything in blue, that is the target. Target median plus 1 standard deviation, and target median minus 1 standard deviation. Everything in red, that is the median of the suite. That is the median of the 7 motions that were selected to fit the target. So in red, the middle one, that is the median of the suite. The one on top, that is the median of the suite plus 1 standard deviation. And then the lower red, that is the median of the suite minus 1 standard deviation. And if you go over these, if you click on different suites, you will see the different results for each suite. If you select a certain suite, on the bottom, you can see the name of the motion, the scale factor, like how much was this motion scaled, and then the PGA, PGV, PGD, and then the duration and further details on the ground motion. And like you can also select these. For example, you see some of them are in gray, one is in green. So depending which one you are selecting, that will become green. For example, let's see. For example, let's assume I want to know which one is this gray motion because it looks really odd. I don't want to consider it in my suite. So I will go over here and start going through these until it becomes green. So it's this one, this recorded in Iran, that is this motion. So probably I don't want to consider that in my suite. So like that is the benefit of looking at these different ground motions. But ultimately, all you want is one reasonable suite that fits your target response spectrum. And you can rank them if you want to manually, like you can add, okay, that's rank 1, that's rank 2, based on your judgment. But you can also look at the median error. So that is the root mean square error relative to the median target response spectrum, meaning it is the median error between the middle red line and the middle blue line. And these are the values. Generally, you would want to have values less than zero point 0.1. That would be an acceptable fit. And then you also have a median error for the standard deviation, because remember, we defined a target standard deviation, which is shown in red. So we're going to compute also the error for the standard deviation of our suite relative to our target. So our suite has the standard deviation shown in blue, and the target standard deviation is shown in red, and we can compute an error between those two. If you are using a design response spectrum from the International Building Code, you will have the red line will be simply down here, values of 0. And thus, really, you should not be considering the standard deviation error or taking that into account when deciding what is the best suite. Ultimately, you should more focus on the median error of your design response spectrum, not the standard deviation, because that's the only target that you defined to begin with. You only gave SigmaSpectra a target response spectrum, so make sure to select it based on the median error of the response spectrum, because you didn't define a standard deviation. So you can go over the different suites, look at the scale factors. You want to make sure you don't have very high or very low scale factors. Scale factors closer to 1 are better, but it's not really a huge problem if you had to go with high scaling factors. But let's look at these. For example, this suite of motions has reasonable scale factors, nothing like 3 is acceptable. It has 0.5, that's also acceptable. And it has the lowest root mean square error, and the red line fits on average the blue line. So I'm gonna consider that as my ideal. To export it or to save it, you click on this export over here, and it should turn it into green. You can see it's now green. And then you go to the lower bottom right side, you have this export suites. You click export suites. And that will allow you to export the details of the suite into a CSV format. So you click CSV, you can name it, you can select the path where you want to save it. Just click OK, and that will save the suite that you selected as being optimal for you to use it in the 1D side response analysis. So let's look at the results. So that is the suite I just exported. The summary file will provide you with the root mean square error. Make sure to report that in your project, because that indicates how well does the selected suite of motions fit the design response spectrum on average. And then you have the name of the individual events, their scale factors, and then further details. And then you have the periods and the response spectra of the individual events and their median, which you will also need to plot the results in your report. An alternative to exporting things as CSV files is to export them in strata format. Remember, we will use these motions to perform 1D strata response analyses. And a nice thing about SigmaSpectra is that you can export these in strata format, which is the third option, strata suite file. If you select this, again, you can name it, select the path, click OK. What I will show you in the second presentation, when using strata to perform 1D strata response analysis, you can simply select this file that we just saved to get the input motions without having to manually or individually add them one by one. So that is the file that got saved as strata format. And then when showing the demonstration for strata in a different presentation, I will show you how to import this file to get the suite of motions, and that will make things much easier instead of having to import the motions one by one. But make sure to export both CSV format and strata format. You will need the CSV format to report results, to plot them in a nice format to include in your report, but you will also need the strata format to use them as input into strata when doing the 1D strata response analysis. And that concludes everything in my presentation, and thank you very much.